If we take an open jar into space, to outer space, and close it once up, thereby filling it with the vacuum of space, what would happen if we bring it to Earth level atmosphere and even into the International Space Station?
It would be the best vacuum we would have ever encountered on Earth, ever. Oh, by the way, you might ask if, quote-unquote, nature abhors a vacuum, which of course it doesn't because most of the universe is vacuum. How come all Earth's atmosphere doesn't just rush out into the vacuum of space?
It's true.
Why doesn't it? Yeah, because Earth has gravity, and the gravity keeps the atmosphere separate from the rest of the vacuum of space. That's all.
Okay. All right, here's the question. I just discovered...
Wait, did I just say that? No, so...
Oh, wait.
No, a vacuum... I should have answered that completely differently.
Yeah.
So...
What pressures were present? Maximum end vacuum pressure 0.020 mbar. Refco rotary vane vacuum pump. Air pressure 1013.25 mbar. Beaker at ground level. The chamber starts at 1013.25 mbar and finishes at 0.020 mbar. Maximum vacuum. The pressure difference is 50,663 times. When the pump is switched on, the air pressure decreases and the liquid particles of water change to gas particles of water. The gas particles move randomly in all directions and will follow the second law of thermodynamics and immediately diffuse or spread out throughout the shape and volume of space defined by the material boundary of the container. This is a simplified description of the processes and the forces and energy involved. Remember, the downward force on the water droplets, termed by consensus as gravity, could not overcome the attractive forces between the water droplets and the side of the glass, which resulted in the water droplets remaining stationary. Both the combined strength of the attractive forces between the water droplets and the side of the glass and the downward force cannot prevent the water gas particles from leaving the open container when a decreased air pressure is produced. The average atmospheric pressure at sea level is 1013.25 mbar. The pressure in interstellar space is approximately 0.000000000000133 mbar. Space is 0.000000000000133 mbar. Earth's atmosphere is 1013.25 mbar. The difference in pressure is 76 quintillion, 184 quadrillion, 210 trillion, 526 billion, 315,789,474 times. You know exactly what that means. The water in the chamber was under approximately 50,000 times less air pressure, 0.02 mbar, compared to when under normal atmospheric pressure, 1013.25 mbar. And you saw that the force of gravity cannot prevent the loss of water from the beaker. Applying the same scientific principle here, no matter how uncomfortable, we know what must happen to the Earth's atmosphere and liquid water. If a low-pressure region, such as space, existed next to our atmosphere, clouds would not be possible. The seas, oceans, rivers, lakes, and other water bodies would also not exist. We would not exist. Please check out the experiment for yourself. Do not take my word for it. First, go to your local school. The science department will have a vacuum chamber and pump. 2. Buy one. See below or look for a good deal on eBay, etc. Or 3. Contact the Action Lab on YouTube. They use their vacuum chamber to do many interesting observations. I know. There is nothing I can say. In my imagination, it was full of such potential and promise. Its existence is not supported by the scientific method and the known laws of science. Where does that leave us? Looks like there are a couple of options available. 1. Become a science denier and state that the second law of thermodynamics is incorrect, even though you cannot prove it is incorrect using the scientific method. 2. Smile awkwardly, ignore this evidence, and keep on believing in an ever-expanding universe, but don't think what it could possibly be expanding into. 3. Do the test for yourself and start a wondrous journey of self-learning and understanding. 4. Start asking difficult questions and be prepared for some difficult answers, or no answers whatsoever, and just more difficult questions. Where now? Now it gets interesting. The water under reduced air pressure observation. Dr. John D. in the kitchen. This video is dedicated to Nathan Oakley and the Flat Earth debate. I cringe when trying to remember how many times Nathan has had to repeatedly explain the concept behind this observation. I felt inspired to do a simple video that will hopefully be a visual guide. The video clip you are about to observe demonstrates the effect of reduced air pressure on liquid water. Main observations. 1. The liquid water droplets on the side of the glass beaker gradually became smaller in size over time. 2. After a couple of minutes, the liquid water droplets could no longer be seen on the side of the glass beaker. 3. The glass beaker on the outside of the chamber still had water droplets on it after the observation. This was to show that the evaporation of water due to temperature was not responsible for the observed loss of water from the side of the glass beaker inside the chamber. What happened? The vacuum pump reduced the number of air particles in the chamber, which caused a decrease in the air pressure inside the chamber. A decrease in air pressure meant that less air particles were striking the water droplets per second, decreasing the air pressure on the liquid water droplets. The attractive forces between the liquid water particles of the water droplet and between the liquid water particles and the glass were still present. Due to the reduction in air pressure, the liquid water particles with enough kinetic moving energy overcame the attractive forces and became water gas particles. The water gas particles spread out throughout the chamber, filling the available space. Attractive forces. For a full and accurate description, please look up intermolecular forces. Note: water molecules will be termed as particles. The water droplets on the glass were stationary because the forces on the water droplets were balanced. The downward force, termed by consensus as gravity, was not strong enough to overcome the attractive forces between the water droplet and the glass and the attractive forces between the liquid water particles themselves. Stationary water droplet indicates the forces are balanced, or equal. There are attractive forces between the water, H2O particles, in the water droplet. It is these attractive forces between the water particles that results in the formation of a water droplet. The red lines represent the attractive forces between the water particles. To know more about attractive forces between water particles, please search hydrogen bonding. Although each liquid particle has kinetic moving energy and is moving and rotating, the kinetic energy possessed by the majority of liquid particles is insufficient for the particles to break free of the liquid water droplet and become gas particles. To gain an understanding of this concept, see the Maxwell-Boltzmann energy distribution for particles. To become a gas particle, a liquid water particle must possess enough kinetic energy to overcome the combined force of the attractive forces between the liquid water particles of the droplet and the force the air pressure exerts on the liquid water droplet. When the air pressure is reduced by the use of the vacuum pump, then the force the air pressure exerts on the liquid water droplet within the low-pressure chamber is decreased. When the air pressure is decreased, the kinetic moving energy of the individual liquid water particles is now enough to overcome the combined attractive forces between the water droplet and the glass, the attractive forces between the liquid water particles themselves, and the now decreased force of the air pressure on the liquid water droplet, resulting in the formation of water gas particles. In accordance with the second law of thermodynamics, the water gas particles will diffuse, spread out, and fill the available space of the container. When the vacuum pump has been switched on for a short time, the liquid water droplets can no longer be seen on the side of the glass beaker. The water has changed state and has become a gas and spread out into the available space.